Welcome to lecture 11. So, in this lecture I will be talking about SPIM, a MIPS32 simulator, how you can write programs in SPIM, which is a MIPS32 simulator. Let us start. So, as you all know, the best way to learn any assembly language is through a simulator, and we should start coding. So, how to start that? We need a simulator which we will be using, that is SPIM, which is a self-contained simulator and it is available in public domain, and you can download that from this particular web page. And this SPIM implements almost the entire MIPS32 instruction set along with the extension with pseudo instructions. What do you mean by pseudo instructions? I already discussed about pseudo instructions. Like in MIPS, there are limited number of instructions. If you want to have an instruction that performs certain task, then you have to use those existing instructions to execute this. There is no move, but you can have move using some kind of pseudo instructions. So, pseudo instruction is move is a pseudo instruction, but that pseudo instruction can be performed using add. We add a value to another register with 0. So, that value will be transferred to another register. So, these are pseudo instructions. SPIM has both terminal based and window based interfaces which is available. It is up to you that which one you will be using it, and SPIM is copyrighted by James Larus and distributed under a BSD license. So, we must know what a SPIM can do. It can read and execute a assembly language program for MIPS32, that is what we need for this particular course, and provides a simple debugger, and it also provides minimal set of OS services, not all, minimal set of OS services via system calls. Through system calls, those OS services can be provided. This is a screenshot of a Qt-SPIM. So, if you install Qt-SPIM in your machine, you will be able to see a view like this. Here, these are the registers which are having different values, and what are these? These are the hexadecimal addresses of the instruction. These are the hexadecimal addresses, and what are these? This is the instruction after encoding. So, these are the list of instructions, and this is the encoded form of this instruction. We have already learned how we can encode a particular instruction, knowing how many bits of registers are present, etc., etc. So, this is basically the main instructions that are getting executed. This is the encoded form of the instruction, and this is the memory addresses. And you can see the memory addresses will be incremented 4, 4. It is a 32-bit instruction. So, all the it is byte addressable. So, it will be added plus 4. Now, let us see the MIPS32 assembly code layout. It has got a text section, it has got a data section, and in this section we have something called global main, GLOBL main. So, this actually shows the starting point, and the starting point it must be global. And now, this is dot global main, and main is the label from where your program execution start. So, if you do not give this in the program, it will be wrong. So, you have to mention that it is global, your main is global, and this starts from a particular label, that is main. and then you can write the user program code here. For any program, you must have some data, and the data portion is written in this part. These are some assembler directives. Dot text, it specifies the user text segment which contains the instructions that are required to execute that particular program. We will see some examples in course of time. Dot data, it specifies the data segment where we put all the data that will be used in our program. And this global main, global GLOBL, global SIM, this specifies what? Of course, this is the global starting point definitely, but this symbol is global and can be referred from other files as well. So, from any other files you will be able to access this. Next is dot word, that is W1, W2, Wn. It stores the specified 32-bit numbers in successive memory words. So, by successive memory words, what do we mean is, let us see. Let us say my address starts, it is a hexadecimal address, and the address starts from 0, 0, 0, 0, 0, 0, 0. Your next address will be and so on. This is how it will go on. So, it is increasing in +4 and so on. So, a word is a 32-bit. If your first word is stored in this location, let us say you have stored some word that is 30 in this particular location, then the next word will be stored in the next location, that is 31 will be stored here, 32 will be stored here, and so on. Half specifies a 16-bit number in successive memory, but it is a 16-bit. Byte, again byte stores a 8-bit specified number in successive memory bytes. We can also specify characters. So, ASCII and ASCII Z are the two directives that are used. It stores the specified string in memory, but do not null terminate it. So, it is not null terminated. A string is null terminated by \0 this n. So, it is not null terminated. ASCII Z str, it is specified as string in memory and it is also null terminated. So, these are the directives that we will be using in this program. When we write a SPIM program, we will be using the following directives. Dot space n, it reserves a space for n successive bytes of memory. Now, register naming convention, we already discussed about all these things, and this is how it is named: $V0, V1, A0 to A3, T0 to T9, S0 to S7, GP, SP and RA. As you know, MIPS pseudo instructions, as discussed earlier, are all supported by SPIM, and SPIM converts these into MIPS32 instructions before executing them. So, we can write a program using pseudo instruction, but this pseudo instruction in turn gets converted into MIPS32 instruction before it gets executed. Now, operating system interface, that syscall is used. See, when syscall is used, you see, when we want to get a value from the keyboard, your keyboard is a hardware device. So, when you want to get that value from keyboard, then you are actually getting the value from keyboard, meaning you are entering something and there must be something happening which takes this value and you see that value in the monitor. Okay. So, there are two things, one is getting the value from the keyboard, which is a hardware, and displaying the value into the monitor, that is also a hardware where you are displaying it. So, in such cases you need to do syscall. So, printing an integer, if you want to print an integer, you have to put the argument in A0 and you have to put the code in V0 1 to print an integer. Similarly, for printing a string, you need to put the code 4 in V0 and the address of the string in A0, and then you can execute it. This is for printing, that means once these values are put in V0 and then you perform a syscall, then it will print, that means on the screen this value will get displayed, either an integer or a string. Similarly, reading an integer, it will read from the keyboard, and then after reading from the keyboard, it must store it in some place. Where it will store? It will store it in $V0. Similarly, read string, the code is 8 and in A0 the address of the buffer where you want to read it, that will be given, and how much length string you want to read, that is given in A1. Also, the code for exit is 10, and after putting the required value in these register, you have to do syscall. Other system calls for floating point numbers also exist, which is not included here. Let us take a sample program. Let us see how this program is executed. So, dot text, in the dot text we write dot global main, and from main is the label from where my execution of program starts. So, what this program is actually doing? Let us also look into the value. What is this value? Value is also a label which consists of some word, and each word is of 32-bit, and what it stores? In the first location it stores 50 and in the next location it stores 30, and the result will be stored in last location, which is initialized with 0. Now, just see this LA meaning load address. Load the address from value and store it in T0. T0 is a temporary register where we are loading this value, address of this value, and storing it in T0. Once I load the address of this value in T0, I need to load the word. What words are present? The words that are present is 50 and 30. So, let us take an example to show this. Now, you see these are my memory location 4A1B03C8. In this memory location I have stored 50. In the next memory location I have stored 30 depending on the value, and in this location I have stored 0. Now, if you see this instruction load address, the address of this value, that means this value is nothing but a label. This label has got an address where this 50 is stored, and from that point after +4 30 is stored. So, this particular address is loaded in T0, and then we are doing load word. We are loading the word from this particular address. What will be this address? T0, the address of value is loaded here, plus 0, we store it in T1. Similarly, the next word, T0 has got the address of this value, T0 plus 0 is this, and T0 plus 4 is this, the next value. So, T0 plus 4 we load it in T2. So, 2 of the numbers, that is 50 and 30, is loaded in T1 and T2. And now I am doing an add, which will add T1 and T2, and it will store back in T3. Now, what I have to do? Finally, I have to store the result of T3 into the location, next location. What is this location? This is the first location which is pointed by T0. This is T0 plus 4, and the next will be T0 plus 0, T0 plus 8. So, this is T0 plus 8 where I am storing it. So, this T3 will be stored here in 8 plus T0. So, again coming back here, that means in T0 my first address is loaded. So, I am just explaining this here, that in T0 I have loaded this address, that is 4A1B03C6. And what is 0 plus T0 then? 0 plus T0 will be the same address which is loaded in my T1. So, in T1 I am loading 0 of $T0. Next, I am loading 4 of $T0. In T0 I have this constant address, but I am adding this with 0, adding this with 4 to get the next address, and after getting the next address, those are loaded in these two registers, that is T1 and T2. Now, my 50 and 30 are loaded in T1 and T2. Now, I am doing an operation which is T3 equals to T1 plus T2. T1 and T2 are 50 and 30, which gets added and stored in T3. So, in T3 now I have 80. Now, this 80 I have to store it in 8 of $T0. So, 8 of $T0 is this location, where after this operation T3 will be stored, where T3 is now 80. So, 80 will be stored after execution of this SW. So, this store word operation will store the value of T3 into this memory location. Now, this is a program that adds two constant numbers specified as immediate data and store the result in a register. So, here we are adding some immediate value. Immediate value means the two values are 0x 2a and 0x 0d. What we are doing? We are adding this immediate value with 0 and then we are storing it in T1. Why? Because we do not have a move instruction. So, instead we are doing directly this here, and then we are again loading this particular data into T2, and then we are adding these two and storing it in register S3. So, these three steps will add two immediate value, that is 0x2a and 0x0d into S3. Coming to the next program, the same program, but using a system call. In this system call, if you recall, if we load 10 in V0, if we pass 10 in V0 and then we do a syscall, then it will exit. So, this particular program is same as the previous one, which is adding two immediate value, but at the end I have to load an immediate number, load immediate into V0. So, in V0 value 10 will be loaded, and once I do system call, then it will get exit. So, it will exit from here. Now, let us see a program, because we have seen many, we have seen not only one system call, we have seen that for displaying an integer in the screen, for displaying a string in the screen, for loading a integer from the screen, for loading a string from the screen, we have so many parameters that we need to load it in V0 and the required parameter in argument, that is A0, and then we have to do syscall. But for exit, we just need to load an immediate value, that is 10, into V0, and then we execute syscall. Now, here you see, read two numbers from the keyboard and print the sum. So, first of all, I have to read two numbers. So, in the data section, I initialize the 3 string, that is string 1, which is enter the first number. Now, see, all these numbers are entered from the keyboard. So, in the data section, this str1 specifies enter the first number, str2 specifies enter the second number, and str3 specifies the sum is equals to, and then the sum will be displayed. So, first of all, I have to print this enter the first number. After printing this enter the first number, I have to get the value from the keyboard. So, first I have to display this enter the first number, and then once it is displayed, I need to read a value from the keyboard. Let us see how we can do this. So, the execution start from main in the .text section .global main, li we load in V0 4, 4 is the value to print the string, and in the argument we load that particular string, load address of str1. That is how this particular thing will get loaded. str1 is loaded in A0, and then we do a syscall. So, after doing this particular thing, what is displayed in the monitor is enter first number. When you run this, it will show enter first number. Now, after entering first number, then I have to read that integer. So, for reading that integer, we have to load an immediate value, that is V0. In V0, we have to load 5, and then we do a syscall, and this syscall will make the data available in V0. So, my data is available in V0, and I do a move instruction, which is a pseudo instruction, or of course, LA and LA, all these are pseudo instruction. So, V0 will be moved to T0. Now, my entered number is in T0. So, using these statement, what we have done? We have entered the first number, we have displayed this enter first number using this part, and then we have entered the number from keyboard through this part, and we have stored it in T0. Next, we load an immediate value $V0 4, and we load the string, the next number, enter the next number in A0, and we do a syscall. In a similar fashion, I load in $V0 5 to read the integer, the next integer from keyboard, and then we move the next integer into T1. So, T0 and T1 is now having, T0 is having the first number and T1 is having my next number. Two numbers are now there. Then I will just add, where I will add T0 and T1 and store back in T1. and now I will display the result. Again, for displaying the result, I have to print the sum is this. So, I am doing here, I am loading an immediate value 4 and the string str3 in A0, and I am doing a syscall. This will display the sum is, and for displaying an integer into the keyboard, what we need to do? For displaying, I have to load 1 in V0. So, 1 is loaded in V0, and then the number that needs to be displayed. Now, we can see that my result is stored in T1. That particular thing I have to load it in $A0 in the argument, and I do a syscall for displaying this integer. And finally, I do load 10 in V0 to exit. So, this is a program that reads 2 integer from the keyboard, perform addition and store back the result in another and displays the result in the keyboard itself. Now, let us see how we can do some other programs like adding 10 numbers. So, till now we are talking about simple programs, loading a value, adding those values, storing it back. But loops and other things are very common in programming. So, we often encounter loops everywhere whenever we write a program. How loops will be executed using this SPIM, how we can write loops using SPIM, we will be seeing it now. So, we will see how we can calculate sum of 10 numbers, and the 10 numbers are stored in consecutive memory location, and these 10 numbers will be added and stored back in another memory location. Or we can simply add this number. Let us see how we can do this. As you know that for any looping, we need to have a counter. So, we need to have one counter that will start from here. If it starts from 0, it will go till 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So, less than 10. If you start from 1, it will be less than equal to 10. Now, these are stored in memory and the label is num. So, what I have to do? I have to load the address of this num first. So, I am doing load address in $T0 num, and then I have to initialize some counter. We need to store the sum somewhere, and another counter, another variable we need for this counter. So, load immediate, we have to load an immediate value that is 0 to T2, and we have to load another immediate value 0 to T3. So, one is where we will be storing the sum, and another is the counter variable that will go starting from 0 till 9. Then in the loop, what we are doing? What basically we need to do? We need to add these numbers. So, what I have to do? First I have to get this number, store it somewhere, again get the next number, add it, store it somewhere. Then I have to get the next number, add it, store it somewhere, and go on doing it till this number. So, for doing so, first of all I do a load word. I am loading the first word in T1, and then where I am supposed to keep the sum in T2. I am supposed to keep the sum in T2. So, I am adding T2 with T1, because in T1 I have the first number. I have loaded the word from 0 of T0, that is the first number is 1, which is in T1. I added with T2 and store back in T2. After doing so, what I have to do? I have already done for one number, then I have to move on with the next number. So, moving on with the next number, I will add to T3 because one counter it has already gone, it will become 1, and then I have to also go to the next location. For moving on to the next location, I have to add 4 to this T0. So, T0 will be added with 4 and stored back in T0, and then what I will be checking? I will be checking whether my T3 has reached 10 or not. If T3 has reached 10, however, I will be checking with branch if not equal. So, branch to this particular loop if T3 is not equal to 10. The moment T3 will be equal to 10, you go to the next statement. So, here when I come here for the first loop, for the first time T3 is now 1. So, 1 is not equal to 10, I go to the loop. I go to the loop, take the next value, add it, again do the same thing. I increment T3, I increment T0 by 4, and then again I check. I do this 10 times. When T3 becomes 10, so I have already done for 10, it will come out of the loop. That means, I have already added, and now my sum is available in T2, because at every time I am adding it with the value of T1, where I am loading the word from next location. So, T2 contains finally the sum, and finally we exit. So, here we are not displaying the sum. In the similar fashion you can display it. You have to load a particular value in V0, a particular value in A0, and then you have to do a syscall to display this value. You can do that as well. The next example is another program which checks if a given number is palindrome or not. So, what is palindrome? A palindrome is a number, if you reverse the number, it will be the same. So, if you have a number 212, if you reverse the number, it will be first 2 will come, then 1 will come, then 2 will come. So, both the numbers are same. Now, let us have a number 1, 2, 3. Is this a palindrome number? You reverse the number 3, 2 and 1. This is not a palindrome number, because this is not same as this. So, this is what a palindrome is. Now, we will see that, we will consider this an example. Let us take an example 1, 2, 3. Basically, what we need to do, we need to extract the last digit, then we need to extract the last digit, then we need to extract the last digit, and while doing so, we need to multiply it with 10 and add it with the extracted digit, and we store it. Whatever we get, again we multiply with 10 and add it with the last digit, that is the remainder. So, firstly let me explain the concept. If we consider a number 1, 2, 3, we take the remainder of the number. So, the remainder will be 3. So, we have extracted the last digit. So, 123 mod 10 we get 3, which is the remainder. So, initially you have to take a counter which is 0. So, the counter is 0. So, we multiply 0 with 10 and we add with the remainder. So, we get 3 here. So, this is the 0th one. So, 0 into 10, initially the counter was 0, it has multiplied with 10 and added with 3. Now, my counter is 3. And what I do, again we need to get the quotient. So, 123 divided by 10, we get 12 as the quotient. Now, we take this 12 again we take the remainder, we get 2. Once we get the remainder as 2, the previous counter value was 3. We multiply 3 with 10 and we add it with 2. We get 32. Now, my counter has changed to 32. Now, how many times you will be doing it? Till you get a 0 quotient. So, again for the next time the quotient is 1. So, 1 mod 10 it becomes 1. Initial counter was 32, then we have to do 32 into 10 and I add with 1. I add with 1 and we get 3 to 1. Now, 1 divided by 10 which is 0. So, we will not continue. So, we got the value which is the reverse of this 1, 2, 3. So, initially we have taken 1, 2, 3. We repeated certain steps. We kept a counter. In that counter we were storing the reverse value and finally, we got the value 3, 2, 1. So, 1, 2, 3, the reverse is 3, 2, 1. But now, this is not equal to this. So, it is not a palindrome. Let us see how we can code this using Qt SPIM. So, here similarly, we have to enter a number and there should be 2 messages. If it is a palindrome, it should display palindrome. If it is not palindrome, it will display not palindrome. Now, first of all, this message enter the number should come. So, we load 4 in V0 and the message in A0 and we do a syscall. Then we enter the number. So, we load 5 in V0, we do a syscall. The value, the number in entered is stored in V0, which is moved to T0. We also move the value T0 to T3. So, T3 and T0 both contains my number for which I have to check whether it is palindrome or not. Now, I am loading an immediate value T2, where in T2 I am keeping 0, I am initializing it with 0. So, the same process which I have explained, I am doing it in a loop. So, what I am doing? Initially the counter value is 0. So, 0 is multiplied with 10 and it is stored in T2. Then my number is in T0, the number for which I have to calculate the palindrome is in T0. I divide it with 10 and I get the remainder in T1. So, my remainder is now in T1. I divide it T0 by 10, I get the quotient in T0. So, T1 contains the remainder and T0 contains the quotient. Now, what I will do? Now, I am adding the counter T1 with the counter value, that is T2, and I am storing back in T2. Next, what I am checking? Whether T0 is equals to 0 or not. That means, my quotient has become 0 or not. If my quotient has become 0, then I will not loop it. So, branch if not equal. If T0 is not equal to 0, again you go to the loop. Now, you are taking the updated value of T2, which is depending on the last digit. So, that last digit is multiplied by 10 and stored in T2 again. Similarly, for that value T1, again for that value T0, we will be dividing it with 10, we get the remainder, we divide with 10, we get the quotient and we again add it. So, we keep on doing this until we get this T0 as 0. That means, the quotient until the quotient becomes 0. Once the quotient becomes 0, then we check the next thing. What we are checking? See, in the first step, we have also stored the number in T3. Why we have stored the number in T3? Because we have to finally check whether the number is palindrome or not. We first reverse that number, and now I am checking whether the number is palindrome or not. So, T3 is checked with T2, that is the counter that I have kept. If it is not equal, then you go to a label NP, that is not palindrome, and where you load this message that this particular number is not palindrome. But if it is not, after this, if it is not equal, then only we are going here. Let us see if it is equal, then this statement will not get executed, and we will directly come to this statement, where we will display the message the number is palindrome. So, just see what we have done, and then we exit it. So, we have put one exit here, one exit here. Why? Because if it is not palindrome, it will come here, and then the exit code it will encounter here. But if it is palindrome, then it will go here, and then it will also exit with this particular code. So, now this code actually shows whether a number is palindrome or not. So, we have written a assembly language code which shows a number is palindrome or not. So, these are function calls in MIPS. Function calls in MIPS, it uses jump and link instruction, we call it JAL instruction, and what it does, it jumps to a label and it stores the PC value in the return address register $31. And once the control, after the subroutine is executed, it has to return back to that particular place. So, returning back to that place, it has to do JR, jump return to RA. Automatically, it will go to that particular address. It will load the previous value of PC which was stored, and it will go on executing it. So, this is a simple example of function call. So, two numbers are stored in these two locations. So, we load these two numbers here, load word from num1 and num2 in these two register T0 and T1, and then we are doing a jump. We are doing a jump and link, where we are going to sumfunc, and in sumfunc we are adding T1 and T0 and storing in T1. And what we are writing here after this execution of this, we are writing jump to return address, that is RA. So, it will load that address and it will come here, because the PC value initially when you have accessed this PC value, then the PC value was incremented to the next one, which was pointing to SW $T1 comma sum. But now you have executed a JL instruction where it has moved here. It will execute this particular instruction, and then it will jump to return address, and it will get the return address from register 31, which is $RA, and it will execute this statement now, starting from this statement. Now, the PC value will be loaded with this again after execution of JR $RA, and then these two instruction will get executed. So, this is how function call happens in MIPS. So, now we have come to end of module 2, and in module 2 what we have learned, we have seen generally what is the kind of instruction format, addressing modes that are there, and then specifically we have gone into MIPS, the details of MIPS32 instruction set, and we have discussed about MIPS32 architecture, and we have taken a simulator, that is SPIM simulator, where you can write programs using this assembly language. Assembly language programs can be written. Thank you.